Oh, yes. All right. You guys did learn how to find domain restrictions and fractions before. And so this will be a quick reminder. I'm not going to talk about it much today. You'll see it in our notes. We'll actually kind of more address it tomorrow just for time's sake. What is the domain of our fraction? But when you see this question on your worksheet today, you actually could have already answered this. And that is that we know that our denominator cannot equal 0 in a fraction. So I see that x cannot equal 5, which would be from negative infinity to 5. And 5 to infinity. So we just break at whatever it can't equal. Sometimes that's more than one thing. So if I were to factor this, I would get x plus 5, x minus 5. Or if I had solved by square rooting, I remember the plus or minus on there. But then I find out that x cannot equal negative 5, but it also cannot equal positive 5, which means I have 2 breaks in my interval from infinity, negative infinity to infinity. We did utilize number lines. If that is something you want to continue using, do that, or just know that you break at each of these numbers starting at your lower ones. So negative infinity up to negative 5, negative 5 to 5, and 5 to infinity. Now I not tried to trick you, but we will see this again later. And so I want to make sure that we address this. Yes, I would set the denominator equal to 0 to figure out what it can't be, right? Oops, x squared plus 25 cannot equal 0. As I go to solve that one, is x squared plus 25 factorable? No. No. What's stopping us from factoring that? The plus, right? The plus, we can't factor it. So I would maybe try solving by square rooting, but when I'm doing that, okay, well, what's that going to give me? Imaginary. So it's saying that our domain restriction is imaginary or not real. There isn't a real domain restriction. There is no number in the real numbers from negative infinity to infinity that I couldn't plug in here, because none of those will give me a 0 down there. Think about it. Plug in negative 10. When I square it, I get something positive, and then I add more positive to that. Would that ever equal 0? No. So I don't have to worry about anything. I can plug in anything, and if we don't have a restriction, that means all real numbers. Negative infinity to infinity is our domain. We will run into one more like that today, where we end up with something in the bottom that looks like a fraction, looks like it should have a restriction, we should have an issue, but because it's an x squared plus, we will not. Questions? Yes. In the numerator, because the top of a fraction can be anything, 0, negative numbers, positive numbers, so we don't have to worry about what's going to show up in the top of the fraction. With a fraction specifically, the only thing we have to worry about is that our denominator is not 0. Kind of like with a radical, the only thing we have to worry about is the fact that it is something 0 or bigger positive. Greater than, we would use the greater than or equal to in a radical. And we would use just a greater than in a radical in the bottom of our fraction. So the other 2 domain restrictions we had was if it was a square root, that's when I say that it would be greater than or equal to 0. Or if I move that square root to the bottom, that x plus 1 just has to be greater than 0. So those are our 2 other domain restriction rules. We are only focusing on that top one today because our whole section is going to be on rationals, fractions, for the next couple days. We're going to see a big chunk of it today, and then we'll add the last little piece of it tomorrow. So today we're going to focus on things like the vertical asymptotes and the horizontal asymptotes. Most of those show up today. Tomorrow we will add one more type of asymptote to that list to be able to graph all rational expressions. And that's where we're headed, is graphing these. We will do this without a calculator. It'll be, again, one of those things that if you had a scientific, you could use that to help you with like some mental math. But no graphing calculators for this, okay? So what I'm going to do is walk us through the step-by-step process of what we look for when we're looking at a rational expression and how we start the graphing. The very first thing you do is not listed up here, but you factor your expression and look for things that would cross off, okay? So anything that would simplify out of our fraction is what is called a removable discontinuity or a hole in our graph. And that's the number one thing you look for when graphing a rational expression. We factor it, we look for something that crosses off. So as I look at this, remember how we simplify rational expressions is we look for duplicates. If I have a pair in the top that matches something in the bottom, like an x plus 2 and an x plus 2, that I am able to cross those off, well, that means something to us now as we graph. That means it's going to be a hole in that location. So two things, don't lose what you crossed off, but also rewrite for yourself what is what I call the leftovers. Okay, so then how do we find this hole in our graph from what I crossed off? Well, it's an ordered pair. A hole is going to be a dot on our graph, so an x comma y. And it comes from this. The x part of it comes from what we crossed off, set equal to 0. So we crossed off x plus 2. So to find the x here, I set that equal to 0. X plus 2 equals 0. Solve for x. And it tells me that the x I'm going to put in there is negative 2. The other part of it, because it's an ordered pair, is the part I will tell you right now that everyone tends to forget, is the second half of a hole. How do you find the y value? You plug what you just got into the leftovers. So this is our leftovers, right? This guy right here is what we use to find the second half of the hole and everything else for the rest of the problem. And so we'll take that negative 2 and we plug it into the leftovers wherever there was an x. Okay, well, negative 2 minus 1 is negative 3. Negative 2 plus 5 is positive 3, and that would simplify down to negative 1. That's how we find the location of it, how we make a picture of it. Is I go to that location in my graph, left 2, down 1, and I put an open, clearly open dot. An open dot. Now, my people out there that have tiny little handwriting, sometimes your open dots look like your closed dots. You have to be very careful that you clearly draw it as an open dot. Questions on a hole in our graph. Now, if I were to type this into a graphing calculator, the hole is so tiny that it is not visible to us on that. But if I could show you how you could verify that there is a hole there, but we can't actually see it on a calculator. We will show it when we draw these by hand. Okay, moving on to the next thing. After you have located if there is a hole in your graph, the next thing you're going to look for is this concept. And so we're going to talk about this concept before I tell you what it is. We have seen this notation before, right? This is the graph of your basic 1 over x. And if we were to look at that graph as it approaches 0, now we've seen this notation before, but this was always an infinity down here or a negative infinity down here, which meant go to the right or go to the left. You can also approach a particular location. So they're saying approach x equals 0, which would be right here. So as I approach this imaginary line of x equals 0, what is my graph doing? Well, if we're supposed to notice it's doing something different from the left and from the right. So as I approach from the left, notice it has a little negative up here. That's the symbol for approach that line from the left of it. So if I start left of 0 and I start tracing my graph towards 0, my graph is headed which direction? Down, which we know means negative infinity. If I do that same thing from the right-hand side, I get on my graph right of that number and I start tracing towards that number. And this one is headed up as I trace closer and closer to 0. Up, we know, means infinity. Well, what happens is if you're approaching a number like 0 and your graph shoots up or shoots down, it is creating what is called a vertical asymptote. You can see it here drawn as a dotted line, and that's how we will draw them. Again, if I were to type this into my graphing calculator and look, a vertical asymptote is an invisible barrier, which you would not see on a graphing calculator. We will draw it in there for ourselves to show that we know what it is, but it is really an invisible barrier that your graph will approach but never touch. Now, notice that you could have one of them, you could have 0 of them, or you could have many of them. There is no set number of vertical asymptotes. A vertical asymptote is just that, it's a vertical line. So its equation, which you will always have to write it as an equation, will always be of the format x equals a number. That number will be wherever it crosses our x-axis. If you follow the way that I set up to find it, it'll automatically already say x equals that number, okay? So how do we find a vertical asymptote? Well, we find a vertical asymptote, first of all, after we have simplified out anything that can simplify. So we have factored and simplified our fraction. Once that is done, anything that's left in our denominator set equal to 0 will be a vertical asymptote, okay? So I've got a couple examples for us to look at of different ways that this can look. Job number 1 is always just to factor your rational expression. So we got a difference of 2 squares here, x plus 1, x minus 1. Can that simplify? No, there's nothing to cross off, right? So we've done step 1, we've simplified our fraction. Step 2, anything left in the denominator will get set equal to 0 and is a vertical asymptote. So your vertical asymptotes in this particular example would be at x plus 1 equal to 0 and x minus 1 equal to 0, or x equals -1 and x equals +1. They must be written as the equation of a line, x equals for vertical asymptotes. I don't have a graph on here, but if I were to then follow this to graph it, what I would do is just draw a dotted vertical line at that location. So at x equals -1, I would draw in a vertical dotted line. At x equals +1, I would draw in a vertical dotted line. There's an example of 2 vertical asymptotes, because remember, there is no set number of these, 0, 1, many, it doesn't matter. Questions? Okay, so a couple variations on that. Let's look at this next one. Same question. I want you to find the vertical asymptotes. So again, we have step number 1, which is to factor and simplify if it can, before we start looking for vertical asymptotes. So factor and simplify would actually kind of lead you back to page number 1, where we identified a removable discontinuity, or a hole in our graph, which you see happening in this one, right? Same denominator, so we get that x plus 1, x minus 1 happening, but this one does simplify, right? So I can cross off that x, what if I cross off everything in a numerator or a denominator? It is a 1, right? I crossed off everything that was there, which means 1 is what's left over. So in the denominator, we have an x plus 1 left over. This takes us back to the beginning. Remember, that's a hole in our graph, which we already had that conversation, how to find. So now we use what's left over to move on to step number 2. Set anything left in the denominator equal to 0, which would be x plus 1. And we would only have 1 vertical asymptote in this graph, and that it would be at x equals -1. Okay, so back to our warm-up. In our last example of vertical asymptotes, when I go to factor and simplify, does this one factor at all? No, so nothing simplifies. I am supposed to set the denominator equal to 0 to find my vertical asymptotes, but very similarly to our conversation at the beginning, what kind of a vertical asymptote am I finding? Imaginary, which means you don't have one. So very rare. It can happen. I don't have a vertical asymptote in this one, but that's not a requirement because that's imaginary. So it's not a real vertical asymptote. We don't have one. Questions? Okay, that's the first 2 things you graph. The next thing, I did not put this in your notes packet because you already know this. We know this question, right? The limit as our function as x approaches -infinity means the far left-hand side of our graph, right? Look at the left. Now what's happening at the left is different than what we've ever seen before. As I look at the far left-hand side of this graph, wait, it's not shooting up or shooting down. So it's not going to positive infinity or negative infinity. That's unique. what's going to happen in a rational expression is going to flatline somewhere for most of our graphs until tomorrow. So when it is flatlining, we have to figure out what value it's flatlining at. What value is this graph flatlining at? 0 is going to come from your y-axis. It's going to come from some line running through your y-axis. It's flatlining at 0. And so our end behavior to the left is 0. On the right, you'll notice that your end behavior will match, is that they will flatline at the same place. And so our right-hand side is also flatlining at 0. Okay. Why is that happening on this? Well, if you think about, as I plug in really big numbers, the bottom of that fraction is going to get really big. Hello? You guys see any car keys in here? Car keys. I'm not seeing any in her seat. All right. Yep. If you see any, let me know. All right, where were we? 0. Horizontal asymptotes. Horizontal asymptotes. Now, I understand that they share the same word as a vertical asymptote, but it is not the same concept. Vertical asymptotes are an impenetrable barrier. You will never cross a vertical asymptote, but you can cross a horizontal asymptote. The entire purpose of a horizontal asymptote is to show the end behavior of your graph. What is it going to do on the very far left? What is it going to do on the very far right? Where is it going to end up flatlining? In the middle of your graph, it can actually cross a horizontal asymptote. So again, I understand that they share the same word, and we are used to asymptote being something you can't cross, but you can cross a horizontal. There is at most one, okay? All of the ones we have today will have one. We will see the cases tomorrow. We're going to save it for a separate conversation of where we do not have a horizontal asymptote, and then what happens. Now, they are horizontal lines, so your equation will always be, and it always has to be an equation. Horizontal lines are always of the format y equals a number, and again, it will be whatever number it is running through the y-axis at. Identifying a horizontal asymptote comes from this chart, and you are going to get to know this chart very well. So it comes from identifying or classifying your rational expression as little over big, big over little, or same. So how do I make that decision? We look at the degree of the numerator and the degree of the denominator, which you guys just told me that you know how to find because we talked about degree of a polynomial, right, on your test. It comes from your biggest exponent. So find the degree of the numerator, compare it to the denominator. If the degree of the numerator is smaller than the degree of the denominator. Now, many of us a very easy example to follow on this one. That would be like a 1 over x, because this is like an x to the 0 over an x to the first, right? The numerator in the top is smaller than the numerator in the bottom. As I plug in really big numbers, so we go all the way to the right or all the way to the left, think about what's happening. As I plug in 10, I would get 1 over 10. As I plug in 1,000,000, I would get 1 over 1,000,000. Okay, well, if I just handed you 1/1,000,000th of a piece of pizza, what did I just hand you? Nothing, okay? What happens is when the bottom is bigger, it essentially becomes the number 0 as you go to the very, very far ends of that graph, okay? So anytime we would classify our rational expression as little over big, our horizontal asymptote every time will be y equals 0. As you plug in really big numbers, it would essentially become the number 0. Tomorrow, we're going to talk about the next one, which is big over little. Okay, so now I have something bigger in the top than I do in the bottom. X squared over x to the first. So as I'm plugging in numbers, the top of my fraction is getting really big, way faster than the bottom of my fraction, right? Think about plugging in 5. If I plugged in 5, I'd have 25 over 5. As I plug in 10, I'd have 100 over 10, right? As I plug in 100, I would have what? 100,000 over 100. It's getting to be just a really big number, isn't it? And so that continues to happen. As we plug in really big numbers, this just continues to grow really big. what happens that means is you don't have a horizontal asymptote. You'll end up having what's called a slant asymptote, which is going to be our conversation tomorrow. So we will not see any today that will be big over little, which means when you get to your worksheet and it asks you to identify a slant asymptote, you will say none, because we will not see any of those yet. The other kind that we will see today is what's called same, meaning that the degree of the top is the same as the degree of the bottom. So if I had something like 3x squared over 4x squared, it's an x squared over an x squared. Well, as I plug numbers in there, it's growing at the same rate, right? Because it's x squared over x squared. Or think about simplifying that. Those x squareds would cancel each other, right? And so what happens is, no matter what I plug in there and I simplify this, it'll always simplify down to that ratio of the numbers in front of it, because those x squareds essentially will always cancel each other. And you'll just keep getting back to this 3/4, 3/4, 3/4 as we plug really big numbers in there. And so your horizontal asymptote ends up being at y equals whatever the ratio of those leading coefficients is. In this case, this would be at a y equals 3/4. So what do horizontal asymptotes look like? They look like a horizontal line. So if I were to draw in y equals 3/4, it would look like a horizontal line that runs through up at y equals 3/4. Again, it can be crossed in the middle. It's just what our graph is going to end up sliding along as we get to the very right and the very left. So end behavior. After we have identified our horizontal asymptotes, let's go through a real practice here real quick, okay? You guys are gonna be practicing for me. So on our next one, we're gonna classify little over big, big over little, or same. Let's look at that first one. 4x over 2x squared plus 1. Thanks. Little over big, good. All right, go back to your chart. If it is a little over big, it says it's 0, right? Little over big, the bottom's gonna grow faster than the top. We'd be looking at y equals 0 automatically. It doesn't matter what numbers we're looking at, y equals 0. All right, next one, little over big over little, or same. Same. Okay, let's go to our chart. Do we have a horizontal asymptote for same? It's whatever the ratio is. Yep, I'll give you a little practical advice. They don't always write these in standard form. Go find your biggest exponent and you use the number in front of that. So the 4 and the 2 are what we would use. It is the ratio 4/2, which would simplify to just align up at y equals 2. Yep, because we're talking about end behavior, we're talking about plugging in the biggest of numbers. So if I think about the difference between having $1 million in my bank account and $1 million plus 1 in my bank account, is $1 million and $1 million and $1 pretty much the same thing? I could buy a whole, yes. So basically what they're saying is, as you get really, really, really big numbers, the other parts just don't make much of a difference, okay? They become negligible. So we just ignore them as we're talking end behavior. All right, last one, 4x to the third over 2x squared plus 1, little over big over little, or same? Big over little. So that is none. It's going to get to be a really big number, which means it will not flatline anywhere. So there is no horizontal asymptote. That is our whole day tomorrow, is slant asymptotes. Okay. The last things that we will add to our graph will be our intercepts. Intercepts are not new to us. We have already looked at how to find an x-intercept and a y-intercept. We'll just look at them in the frame of rational expressions. X-intercepts always came from setting our function equal to 0. We called them zeros, right? X-intercepts were our zeros, setting our function equal to 0. Well, what it turns out is, in a rational expression, to make it equal 0, your numerator has to equal 0. And so we can kind of streamline our process and just set whatever is left in the numerator equal to 0. So in this case, we would have, well, it doesn't simplify. I just want to show you. This does not simplify. I would check that first. Whatever's left in my numerator, set equal to 0. is a dot on my x-axis. So I would have a dot on my x-axis at -3. Just a note that you can have 0, 1, or many x-intercepts. There is no set number of x-intercepts. Y-intercepts, again, we have done y-intercepts before, and we always found our y-intercept by plugging 0 into our function. That will not change. So I go to my function and I plug 0 in. I would go to the unfactored form if it's an option. You can go to the factored form. It will give you the same answer. And that's a dot on our y-axis, and you can have at most one of them. Any questions on your intercepts? Okay, putting this all together. Now, what you're gonna see is your notes don't quite match mine right now because yours is a little more guided. And here's what I'm gonna tell you. When you go to do this tonight without me, go to this page in your notes because it does a really nice job of breaking it down in the correct order of how to find them and telling you, like, look at this first. So you're going to go down this list that you're looking at right now in your note sheet, and you're going to address number 1. Whether we have it or not, you think about it. And then you move to number 2, address that. You move to number 3, address that. And if you go through all of these steps, because I understand that graphing these is overwhelming, but if you just follow those steps, it will walk you through the process. That is not what I have up on my board because this is eventually what your problems are going to look like, including when we eventually get to our DCA and you have to graph these without the steps, okay? So we'll follow your note sheet here, but step number 1 says, first of all, factor to see if it can simplify. So as we look at this example right here, I would have an x plus 1 over factor x plus 1, x plus 2. Will this one simplify? Right? We have something the same in the top and the bottom. We've already talked about this part of it, but when I cross that off, what's left in the numerator? 1, right? Okay, so before we forget this, remember I'm addressing right now, is there a hole in my graph? Yes, something simplified out of my fraction. So this part, for whatever reason, people forget one or the other of them. How do I find the first part? What I crossed off. So I set what I crossed off equal to 0. And I find out that x equals -1 for the whole. The second part of it, you have to use what's left over. What's left over? 1 over x plus 2. This is what we use for the entire rest of the problem, including the second half of the whole. So our whole starts at -1. I plug that into what's left over to get the ordered pair for that whole. 1 over -1 plus 2 would be 1 over 1 or 1. And I go to my graph and I put a very clearly open dot at -1, 1. Now, for my bad handwriting people in here, you're going to have to slow down and make them pretty pictures because accuracy is a little important on the fact that I just put a dot at -1, 1. Okay, after we have addressed step number 1, we go to step number 2 that says, look for vertical asymptotes. Vertical asymptotes, read again on your note sheet. It says set what equal to 0? The denominator. So whatever's left in our denominator, and again, we only use the leftovers from here on out. So only the thing that's left in our denominator is x plus 2. Set that equal to 0 and solve. Vertical asymptote, any asymptotes, vertical, slant, horizontal, it doesn't matter, have to be equations of lines. So it will have to say x equals. And ours says x equals -2. So I go to -2 and I draw a dotted line vertically because it says vertical asymptote. Okay. Questions on that so far? Now the next question, it should not matter if you do the simplified or unsimplified version of it, you would get the same answer, but is this little over big, big over little, or same? Little over big, right? We have an x to the 0 over x to the first. So I would say little over big. So that's when I go back to my chart and I say, is it horizontal or slant? It's not slant today. So it's little over big. My chart tells me exactly what that is. I know for sure these are mutually exclusive. You can only have one or the other. You cannot have both a horizontal and a slant. Today, we will never have a slant. Okay. So a little over big tells me my horizontal asymptote's at y equals what? 0. Now, when you guys are drawing a asymptote along an axis, whether that's the vertical or horizontal axis, it doesn't matter. Draw it like slightly above or below it so you can actually like see the line, because otherwise it tends to blend in, or use a different color. It doesn't matter. I'm just giving you some practical advice here. But I'm going to draw it like slightly above my x-axis, even though it's supposed to be at y equals 0. Otherwise, I can't see it when I draw it over that axis. Okay. All right, moving on to our intercepts here. My x-intercept, ooh, you're going to see this again today. My x-intercept, if I read in my notes, it says I'm supposed to set what equal to 0? Numerator, but my numerator is currently 1. Okay, if I set 1 equal to 0, does 1 equal 0? No, so that's telling us that you don't have it. So yes, I am setting 1 equal to 0. That doesn't even make sense. So I don't have 1. So I just put NA or none. And then our y-intercept, plug in 0. And put a dot on my y-axis at 1/2. Questions? Okay. To finish our graph, because clearly we don't even have lines drawn on there yet. To finish our graph, you have to understand that your vertical asymptotes are going to break your graph into sections. We only have one vertical asymptote, so I'm only going to see one section on this one. But if I cover this up, if we look at just the right section, so here's my vertical asymptote. Let's look at just the right-hand section. Do I see dots? Yes. That is enough to graph in that section. If you have some dots in there, it's enough to graph it. And so what I'm going to do is, if it is an outer section, which is all we have in this one, because we only have a right and a left. So if it's a right section or a left section, your graph is going to corner. And my dots tell me if it's going to corner above my horizontal asymptote or corner below. And because my dots are above my asymptote, it's going to corner above my horizontal asymptote. So all I do at this point is I follow along my asymptote. Make sure you don't fill in the hole. It is a dot. Don't fill it in as you connect it. Go through any other dot that we have, which is our y-intercept, and slide along our horizontal asymptote. So again, if it's a right or a left section, which again is all we have in this picture, it's going to corner. If I look at the left-hand side of this graph though, do you see how I don't have any dots? And so I don't know if it's going to corner in the top or the bottom of that. And it has no impact on the other side. So please understand that just because you have one above, the other one does not have to be below. They actually don't really have anything to do with each other. So I do just now test an extra point. So if I look at a section and I don't have a dot in that section from doing this, we just have to pick a dot and plug it into our function. How do I pick a dot? Well, look where your asymptote is, find any numbers like right next to it. So like -3 or -4 or -5, I usually stick pretty close by. So I would probably plug in like -3. Okay. Again, it's always going into my leftovers. That's all we use from here on out. And let's see, -3 plus 2 is -1. It looks like we're down at -1. So -3, -1. That tells me we're going to corner below. If you were unsure that you had done it correctly, you can pick another dot. It should fall in the same area of the graph. So like if I plugged in -4, it should also give me a negative number. You don't have to. One should be enough. But if you see here, I get a 1 over -2 or a -1/2, it would also be below. And it's telling me that it's going to corner below. So again, I slide along my asymptote, go through the dot or dots that I have, and slide along my other asymptote. So getting rid of my little screen shade here, there is our entire picture. Now, had I handed you this question during the warm-up, you would have told me that this graph had a break in the domain at -1 and at -2. That does not change. Your breaks in your domains will still be at anything that is a whole or a vertical asymptote unsimplified. And you didn't know that when we started today, and you also told me those breaks correctly. So just so you know, going ahead, and we're not going to spend a lot of time talking domain today because we got a lot to get to, but -infinity to all of our breaks. -2 at our vertical asymptote, a break at -1 for our whole. But this is no different than how you would have found domain before today. Okay? Any questions on that? some people kind of hesitate because once we simplify it, it looks like there isn't a domain restriction at -1. You didn't know to do that before today. So it's no different. You just use the original always to find domain. You will always see in your domain a break at any hole and at any vertical asymptote that we have. Okay, so we need to see some variations. And so basically we have 3 more problems today, assuming we will not get to those because we are gonna run out of time, aren't we? Let's go as fast as we can. Okay. You don't have to have any of these things. As we look at this next example, we have x plus 1 over x plus 2, x minus 2. Does anything cross off in this graph or in this equation? So as we look at step number 1, which is a hole, we only have that if there's something that crosses off. You do need to address that you have looked at it with either a none or an NA. Don't put like a circle with a slash through it. That means empty set. It means something. So we want to put either like none or NA there. But then we just move on. Okay. So as we move on to this one, the next thing we would look at is our vertical asymptote. We have 2 of them. And remember, vertical asymptotes, you can have 0, 1, or many. Anything at this point that is left in our denominator gets set equal to 0. And I see that I have a vertical asymptote at x equals -2. And I have a vertical asymptote at x equals 2, which just then looks like 2 vertical dotted lines in my picture. After that, we go to the little over big, big over little, or same. This is okay, we know this. Remember, the question is degree. If it is factored, that degree can kind of be hiding, right? We would have to think of the unfactored form. What is your biggest exponent had I multiplied it all out? And it would be an x to the first over x squared. That is a little over big. And if again, we go back to our chart for little over big, that means it is a horizontal asymptote at y equals 0. Never a slant today. And I apologize, we're going to go through this as fast as I can so we can see as much as we can before we get out of here. X-intercept is going to be where our numerator equals 0. So at x equals -1. And our y-intercept, we're going to plug in 0. I'm going to always plug into the unfactored form. And we have a dot at -1/4. That's all our dots, right? Now, in this particular picture, we have 3 sections to our graph because we have 2 vertical asymptotes. You have to the right of that vertical asymptote, you have between those, and you have to the left. Our graph on the right and the left will look just like it did on the last page. It'll either corner in the top or it'll corner in the bottom. We don't have dots there though, right? You see that I have no dots in the right-hand section. And so I have to just plug something in there, plug in 3, plug in 4, plug in 5, it doesn't matter, but that will tell us where it's going to corner. So let's plug in 3 real quick here. Again, I'm gonna plug into the unfactored version. Three squared minus 4 would be 5. 9 minus 4 is 5. So we have a dot at 3,4/5. The right-hand side is going to corner above my horizontal asymptote. Pick something to the left of this section here because my outer sections will always just corner. Okay, well, something to the left would be like -3, -4, -5. I'm going to pick -3. -3 plus 1 is -2. -3 squared is 9. Minus 4 is 5. That's a negative number, -2/5. The left-hand side is going to corner below my horizontal asymptote. But the middle section does not corner. It has one of 2 shapes. It will either look like a cubic or it'll look like a parabola. And those can be up or down, it doesn't matter. But how do I get that figured out? I use the dots that are there or plug in more if I need to. I can tell you right now that this one is going to look like a cubic, decreasing cubic, and this is why I know that. First of all, if we have it right here, it is not going to hit the x-axis and turn around and come back. It's not going to just be tangent at that point. If you're unsure, you can plug in like -1.5 and you would see that it is a positive number. But how do I know that it doesn't come down here, hit these points, and then turn around and come back up? If it did that, it would have to hit my x-axis again, but I only have one x-intercept. right? So it can't do that. So it can't hit my x-axis again. Like it can't turn around and come back up. So what that means, I have no choice but to slide along and head down. So this one looks like a cubic in the middle. Questions? Okay. The last one I want to talk about, just because we have not seen it yet, is on this one. And we're only going to look at the very end of this one, and that is that the horizontal asymptote. Okay. This one, if you factor, nothing crosses off. There is no hole in this one. The vertical asymptote, if I set this denominator equal to 0 and solve, subtract 3, divide by -6, I would get x equals 1/2. It's the horizontal asymptote I want to talk about because we've seen two little over bigs. This is an x to the first over an x to the first. That is a same over same. Okay, so that's where we go again to our chart. And on a same over same, it says to use the ratio of the leading coefficients. So our ratio would be 2 over -6. 2 over -6 simplifies into -1/3. And it would be drawn down there about y equals -1/3. Any questions on that? Now I can finish this one super fast because here's our x-intercept, 2x plus 6, that equal to 0. Subtract 6, divide by 2, I get x equals -3. Plug in 0 for our y-intercept. 2 times 0 plus 6 is 6. -6 times 0 plus 3 is 3. 6 over 3 is 2. And so I can clearly see on the left-hand side, I've got dots. So, and those dots are above my asymptote. It's going to corner above. All I would have to do is plug in something to the left, like 1 or 2. If I plug in 1, I get 8 over -3, -8/3 or -2 and 2/3 would be down here. And that tells me that my graph is going to corner below. I know that was really fast at the end there, but you've seen enough to get through. Use your note sheets. Follow that step by step. The only thing we haven't seen is when it is factored to begin with. No difference. So if it is factored to begin with, they've just kind of done the first step for you, which is nice. Your assignment tonight is this worksheet. We'll have a place on Google Classroom for you to turn that in.